Welcome back, Method students. In this section, we're going to go through a few more examples of differentiating x to the power of n, but this time we're looking at cases where n is negative or where it's rational. So similar ideas as in the previous section, where when we differentiate a term like this, we're going to multiply by the power and subtract 1 from the power. We're just dealing with situations where the powers might be negative numbers or they might be fractions, or both. Important little note here, whenever you're trying to differentiate fractions with x in the denominator, it's always a good idea to bring the x term to the numerator and then change the sign of the power. Much easier to apply your derivative rules that way. So let's have a look at this one. This says find f dash of x if f of x equals 5 on x cubed plus 6x. So what we're going to do here first is, we're not differentiating yet, but we're going to rewrite f of x as 5x to the power of negative 3 plus 6x. And that just makes it a little bit easier to see what the power is of x, and now we can apply our rules. So when we differentiate, and because we're differentiating at this step, we're going to call it f dash of x. We're going to multiply by the power. So multiply the first term by negative 3, which will give us negative 15. And then subtract 1 from the power, which makes the power negative 4. 6x, well, that's really 6x to the power of 1. So when we differentiate that and then drop 1 from the power, we know that that just becomes the constant 6, right? Because taking 1 away from that power would make it x to the power of 0, which is just 1. Now, arguably you could just leave your answer like this. This is a correct answer. One of the conventions in maths is often to write your answer in the same form as how it was written in the question. So you might go, okay, well, I'm going to move that x to the bottom and make it a positive power again, plus 6. Okay, so that could be our final answer. Again, technically speaking, you have answered the question at this line here, but that might be a more conventional way of writing your answer. All right, another similar one. We've got a rule y equals x squared minus 1, all divided by x, and we've got to differentiate this. Now, the temptation is to just rush in here and differentiate term by term, but actually, we haven't really got this written term by term yet. So again, we're going to do some rearranging to the original expression before we differentiate it. First thing I'm going to do is I'm just going to write this as two separate fractions. Okay, and that will let me do some cancelling and see what the powers are for each term. So x squared over x just gives me x to the power of 1, and 1 over x is the same as x to the power of negative 1. And again, now I can see what the powers are for each term, so I'm going to differentiate. Dy dx, which is the derivative of y, will equal, okay, derivative of x is just 1, minus the derivative of x to the power of negative 1. Well, if I multiply by the power, I'm going to get negative 1 times x, and then subtract 1 from this power, that becomes negative 2. Now, this is a little bit messy looking, so let's tidy it up. So dy dx equals 1 plus x to the power of negative 2, which of course is 1 plus 1 over x squared. Again, if we rewrite it with positive powers. And as I said in the previous example, technically you've got your answer at this line. So this last step may not be necessary, but certainly an equivalent and correct answer. So again, key point there, whenever you've got some x's on the bottom and you want to differentiate that expression, typically a good idea to try to get those x's up to the top so you can see the power and make it a negative power and then apply your differentiation rule. All right, let's have a look at a couple where the powers are fractions. Bear with me a second, I'll get that in the camera. And so again, same rule applies. We're still multiplying by the power, subtracting 1 from the power. But it is useful to remember this index law, and it's one of the maybe less commonly used index laws, I suppose, when you think about the ones you learn first. But if you have, well, I guess you would read this as the qth root of x to the power of p, then that can be written as x to the power of p over q. And again, writing it in this second form here is going to make it much easier to differentiate because you can see what the power is, so you know what to multiply your expression by, or your term by, I should say. So this one's saying calculate the derivative of square root of x plus the cube root of x to the power of 5 with respect to x. This notation, you've probably come across it before already, but this just means like to find the derivative of that expression with respect to x. Okay, again, before we differentiate, we're going to do some rewriting of the expression. So I'm still going to write the original notation. So the first term, x, the square root of x is the same as x to the power of a half. Excuse me, getting tongue-tied this morning. Cube root of x to the power of 5. Well, if I think about this rule, the power on x goes on the top of my fraction, and the I guess the number or the order of the root that we're taking goes on the bottom. So the cube root of x to the power of 5 is actually the same as x to the power of 5 on 3. Okay, so now I can see the powers of x, and I'm going to differentiate. So now I can drop this d over dx because I'm actually going to be differentiating, so I'm evaluating the expression. And I'm just going to multiply by the power. So first term becomes a half x, and I'm going to subtract 1 from the power. So a half take away 1 gives me negative a half. Now, that's probably one you can do in your head, but it's not a bad idea if you get some tricky fractions to just write it somewhere separately, right? So you can keep track of it. So you could have just said over here, oh, okay, I want to make sure I know how to do a half minus 1. Well, that would be 1 on 2 minus 2 on 2. Yep, that's negative 1 over 2, right? So again, you could have done that one in your head, but not a bad idea if you're ever unsure to just do the working separately. Second expression, okay, multiply by the power. So 5 on 3 times x, subtracting 1 from the power. Again, if you want to make sure, we're doing 5 on 3 minus 1, which equals 5 on 3 minus 3 on 3, which is just going to leave us with 2 over 3. Okay, so the power, after we subtract 1, becomes 2 over 3. Now, again, technically speaking, this is a correct answer. But if we were to try to rewrite it in the form that the question was given in, then we've got a little bit of work to do. Firstly, in this first term, we've got x to the power of negative a half. So we can move that to the bottom and make it a power of positive a half. Could also then write this second term as a fraction. And so we could say that this is 1 over 2, remember x to the power of a half is the square root of x, plus, what will this one be? This will be 5 times the cube root of x squared over 3. Okay, and one last example for this section, and worded a little bit differently, so we're going to have to read this carefully. This is one of those, extra unknown values, and we have to work out what they are. It says the graph of y equals a over x plus bx has a gradient of negative 1 at the point 2, 4. Find the values of a and b. Okay, so we've got two unknowns to determine here. And typically speaking, if you've got two unknowns, you need two pieces of information, maybe two equations to set up so that you can solve for those unknowns. Well, let's see, what do we know? We know that if this graph goes through the point 2, 4, then at some point x must equal 2 and y must equal 4. So that's actually some information that we can sub in straight away. So if we sub x equals 2, y equals 4, that should give us an equation in terms of a and b. So 4 equals a over 2 plus 2b. Okay, so there's one equation that we can use to work out the values of a and b. The other bit is talking about the gradient of negative 1. In other words, at this point, the gradient's negative 1. Now, as soon as we're thinking about gradient, we're going to be thinking about the derivative, because remember that the derivative, which is dy dx in this case, is the rule for the gradient at any point. So if we, actually, before we write dy dx, I'm going to rewrite the original expression as ax to the power of negative 1 plus bx, okay, like we were doing before, so we can see what the power is of that first term. Now we can work out dy dx, and that will be negative ax to the negative 2 plus b, because remember the derivative of bx will just be b. Now let's have a look. Is it going to be easier to rewrite that? Probably. So dy dx equals negative a over x squared plus b. And the question was saying that the gradient is negative 1 at the point 2, 4. So in other words, when x equals 2, dy dx equals negative 1. So we're going to sub dy dx equals negative 1, x equals 2, and that will give us negative 1 equals negative a over 2 squared plus b, which means negative 1 equals negative a over 4 plus b. Now, if we're trying to think about, I suppose we've got two equations here. We want to be able to solve for a and b. Let's see. Well, we might want to just write this equation in terms of b. So I'm going to keep b on one side as a positive number and then just say, well, b will equal, if I add that a over 4 term to the other side, I'm going to have positive a over 4 minus 1. And so if there's my second equation, I'm running out of paper here, so this might get a little bit messy, but what we're going to do is we're going to substitute this back into the first equation. Okay, so maybe I can do something a little bit sneaky like that, give myself some more space. So if this first equation now has a different value of b, we're going to get 4 equals a over 2 plus 2 times a over 4 minus 1. Okay, and now having made that substitution, we've got an equation that just has a in it, so we should be able to solve for a. So 4 equals a over 2 plus 2 times a over 4, which will actually just give us another a over 2 minus 2, so just expanding that bracket there. A half a plus a half a, very conveniently, is a whole a, so 1a, minus 2, and therefore a would equal, if we add the 2 over, a would equal 6. And once we have the value of a, we can then substitute back into this second equation here to find the value of b. So we know that b was equal to a over 4 minus 1, which is now 6 over 4 minus 1, because we know that a equals 6. So what have we got? 3 over 2 minus 1, which is 2 over 2. So b is equal to a half. Okay, and that's our value of a, that's our value of b. We should maybe write that a little bit more clearly. So a equals 6, b equals a half. That'd be our final answer down there. And so that's a really common type of question, right? So a question where you know a gradient, you know a point, so you have to do some substituting to find some extra unknown values. You get lots of those questions in the differentiation topics, so definitely good ones to practice on. Thanks, guys.